Hello computer science students, welcome back. In this video we're going to do some more assembly programming, and in this program we're going to try to again accomplish a task similar to our factorial program. In this one we're going to try to accomplish the task of performing Rot13 encoding. So what is Rot13? It does not have anything to do with decay or bad luck. What it means is rotate 13, that's what it stands for. And the idea is if we assign each letter in the alphabet a value, starting with A equals 1, B equals 2, C equals 3, and so on, then you could, in theory, create a really simple and not that secure encryption where you substitute each actual letter you want with one that's 13 numbers off. In fact, by adding 13. And so, if A is 1, then N is 14. You can count that yourself if you'd like, but it's true. So A1 plus 13 equals 14. That means in this encoding, A would be replaced with an N. Anywhere in a string you wanted an A, you put in an N. N, which is value 14, if you add 13 to it, it's 27. Well, our alphabet only has 26 letters, so you roll around, you rotate around. You can think of it as a remainder, or one other way to think of it is you just subtract 26 if you go past Z. And so N 14 plus 13 is 27. 27 is past 26. We're past the Z. So we're going to subtract 26 from it. 27 minus 26 is 1. So what this ultimately means is, and you can test it for all the other letters, that A transforms to N transforms back to A, and so on. B to O, O to B, C to P, P to C. One really nice thing about this encoding is it's very straightforward. You use the same rules to encode as decode. But it is something that is not really cryptographically secure. It's very easy to solve this problem if you're someone trying to hack in. And so usually the really only practical purpose for this is if there's like a puzzle and you're trying to hide the solution while also showing it on the same page. Let's say you had a word puzzle and the solution was hello. You could say that the solution is URYYB and then explain how to decode using Rot13. So someone looking at the page wouldn't see that the answer is hello, but they could find out if they really wanted to confirm their puzzle answer. So it's used for a really simple kind of non-serious encryption. Maybe you're writing a letter to your friend in class and you don't want the teacher to be able to read it, so you encrypt it in Rot13, and then they pick it up and they say, this is complete nonsense, what are you doing? But your friend knows it's really easy to decrypt, and if your professor is a computer science professor, they may too. But that's the general idea. So it's also important to note before we dive into this problem that we need to be familiar with ASCII. So I flipped over an ASCII table. And so in this ASCII table, we're going to use lowercase letters in our message that we decrypt today, or encrypt. And so we're going to focus specifically on handling lowercase letters. And so you'll notice that in the ASCII table, A is 97, not 1. But the same rule applies. 97 plus 13 is 110. What is 110? It's N. So this matches with our Rot13 that we saw before. It's the same thing. It's just instead of being 1 to 26, we're 97 to 122. And so A to Z will still work the same way. We just have to make sure that when we go past Z, like if we do U plus 13, that would get us 130. 130 is past Z. It's past 122. So we're going to end up subtracting 26 to get its conversion. So this ASCII table helps make sure that we can do this relatively easily in our code as well. So let's dive in. We've already done a few programs to get us comfortable, solved a problem with factorial. Let's stick to the nano editor and work on our Rot13.s. All right. So as with all of our programs so far, and hopefully all that we write in this class, we will leave a comment at the top that says Rot13.s, the name of the program, what it does. So this encrypts / decrypts, D-E-C-R-Y-P-T, decrypts, Rot13 encoding, and name. So there's my name. And we will also start with our dot syntax unified, which is kind of our modern syntax that we use now, and global start, and we'll create our start label. All right, so we've done all the setup we need. Now, a few things we have not done yet. One is use a string at all. So how do we use a string or data other than just integers and numbers like we've been using so far? In assembly, there's an area called data that you can create. You do .data, and this is where you would create variables. Registers are technically not variables. We use them like that in assembly, but if you're really programming with variables, where do your variables actually get stored? Well, they're not actually registers, they're stored in variables, and so that's basically what we're going to do here. We're going to create a variable called message. So we give it the label message. It's going to, the format of it is ASCII. So we do .ascii. So that's telling the computer what I type here should be decrypted. I guess decrypt, I'm getting too cryptography in here. Should be translated as if it's ASCII using the ASCII table. And then we'll create a string. So I'm going to create a string called, that's going to be decrypted, and we're going to try to unencrypt it, decrypt it. And so if you can decrypt it correctly, then we know that it works if you get not gibberish out of this. So it's GUR space CNFF JBEQ space VF space N space FRPERG, and then we're going to put a \n at the end. For those who are not familiar with this, you may have run into it in CS1 or CS2, but you also may not have. In strings, and this is true in Java and in C and in Python and anywhere that you're inside of a string, inside double quotes, there's special characters that allow us to control what happens in the string. \n means new line. So basically what I want to do is at the end of this print our string out with a new line at the end. So that way it's not just there's not other text at the end of our string. It'll just make it easier to see. So anytime you need a new line, you can use \n. All right. Now, something else that we're going to assume is that we know the length of the string. Typically, in whatever language you're in, there is a way to get the length of the string. We're going to assume that way exists and has been used, just to simplify our program a little bit. So let's count how many letters there are to get the length of the string. This will tell us how long to keep looping. And what we want specifically are the letters, how long is the string that we want to decode. So here's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We would not include the \n because we don't want to decode or decrypt a \n. It needs to stay how it is. So how many letters do we want to decrypt? That's 24. So we're going to assume that that information has been loaded into a register, and we're going to simulate that by just typing move R124. So again, there's a little bit of hand waving here, but I promise you that no matter what language it is, your code would have the ability to get the length of the string and could have it stored in a register very easily. So we store the length of the string in R1. And now we have a new command, which is load register, LDR. And so we're going to load register R2 with our message. So how do we do that? R2, comma, equals message. The equal sign means that we are going to point to the address of the message. We'll talk about that again in a little more detail in just a second. And then we're going to loop. We know we're going to need a loop to go through the string and edit each letter to perform this Rot13 encoding on it. So we're going to create a loop label. We'll use another new command, LDRB, which is load a register with a byte. LD load, R register, B for byte. So load a register with a byte. So we're going to load R3 with a byte. How long is a character again? Oh yeah, it's a byte, so that works well. This is the command to load a character. All right, now I'm going to stop for just a second and talk about some of the hidden details here. I mentioned that equals message is the address of message. So if you actually were to look at R2 in the debugger, you would see that it stores an address. And it'll be important to be able to recognize addresses, especially when we get to the bomb lab in a little bit here. So this is the address of message. What does that mean? That means that in memory there's a space where this is stored. And that place in memory starts with an address. For the sake of making things easy, this is absolutely not correct, but for the sake of making things easy, let's say that G is stored at address 1 in our memory. So then if G is in address 1, then U would be in address 2, and R would be in 3, and then a space, and so on, right? So what's actually stored in R2 is not the whole message, it's just the address of the first letter of the message. And so when we do this, square brackets around R2, that says R2 is an address. I want you to go to that address and pull out the data stored there. Well, the string starts at letter G, and I loaded a byte. Each letter is 1 byte. So the byte at address R2 is the letter G, the first time through my loop. Now in future times, if we move R2 along, we'll be able to grab 1 letter at a time for every letter following that. So in this case, we're basically loading the letter G the first time through. All right, well, we need to perform our Rot13 encoding. So I'm going to create a little space here. Blank lines, by the way, do not affect your assembly program. It will be, the assembler will get rid of them and format everything for the computer. For us, we can include spaces wherever we'd like. And so how do we perform Rot13? We take whatever letter it is, and we add 13 to it. Now, we talked about a potential problem we were going to run into, right? The problem could be that if we had like an n, which is number 14, 14 plus 13 is 27, now we're past the end of our alphabet, and so we need to kind of recover from it. So we need to see, did we go outside the range of the alphabet? So let's see, so we need to compare R3 to something to see if we went too far out of our alphabet. What do we compare to? 26. I don't think 26 will work. It worked if we look at just pure Rot13 and we give A1, but in computer science and in ASCII, our lowercase letter string here doesn't start with A equals 1. It starts with A equals 97. So what number tells us we're out of range? Z, or 122, right? If we go beyond 122, we went too far, and we need to correct. So we're going to compare R3 to 122. So there's a couple ways to handle what do we do when we do this comparison. What I'm going to do may feel a little bit unintuitive to you. Let me make a note of this real quick, by the way. Is char less than or equal to z? I'm using less than or equal here for a reason. So how am I going to do this? I'm going to branch if R3 is less than or equal to 122. So that means that we have added 13 to R3, and yet we're still in the range of A to Z. So we're going to branch in that case. And where do I want to branch? Let's go to a new place. I'm going to call it loop 2. We probably could make a better label for this. Maybe it means like branch if less than or equal to letter converted, right? Because if the character is less than or equal to Z, then we're done. We're ready to move on to the next character. And so we'll create an area, a loop, a label maybe called letter converted. So maybe this is a better label. And really, if we wanted to, and maybe what's better here is instead of using loop, let's use next letter. Maybe these are a little bit more meaningful to us. So the label here is going to be next letter. If the letter is, after adding 13, still in our range, then we move to letter converted. Otherwise, we finish the letter we're currently on, which means that we need to subtract 26. So that means we need to subtract R3, 26. So if not, then subtract 26. So let's pause for a moment. So we read in a letter, is the letter after adding 13 less than or equal to Z? All right, let's again translate what that means. So A plus 13 is 110. That's N. N is 110 is less than or equal to 122. So we move on to the next letter, essentially. B plus 13 is fine. All right, everything is fine up until n. N plus 13 is 123. 123 is not less than or equal to 122, so what are we going to do? We're going to subtract 26 from it. So then let's just make sure this works. What is 123 minus 26? It's 97. So that works out well, right? That translates us back to A. So this should work for all of our letters. Okay. So our next letter loop is done. Now our letter is converted. So what do we need to do? We've converted our letter into R3. We now need to make sure we save it back into our string. So we've taken the G, we've converted it. In our case, what would the first letter G convert to? Let's look at this table. G would convert to T. And so now we need to store T in our output string that we're going to end up using later. So how do we do that? str for store, and then B for byte. We're going to store a byte from register 3 into the address pointed to by register 2. Again, register 2 is pointing at the first address in our string here, so we're going to overwrite the G with our converted letter. We then move to the next, so that's done. We're done with that letter. We're moving on to the next letter. So we're going to add to R2. Again, where are we in our conversion string here? We're going to add 1 to it. So we're going to move to the U. We're going to subtract 1 from the length of the string, or really this is how many more letters do we need to convert. So we subtract 1 from that, we've converted 1 letter, and then we compare our R1, how many letters do we have to convert left to convert to 0, and if we still have more letters to convert, so if we're not equal to 0, then we move on to the next letter. Right, so branch not equal to next letter. Right, so if we had 24 letters to convert, we went to 23. Compare 23 to 0. If it's not equal, move to the next letter. So this means we'll keep looping until, it's kind of like a while loop really, until there are no more letters left. Okay, so this is our loop. This will allow us to go through all the letters in our string. And then we need to figure out how do we actually print the string. Because we haven't talked about that either. So how do we print to the string to the screen? All right, we have to make use of some registers here. So R7, we've been putting 1 in it, which means end our program and return an integer. Here we're going to put a 4 in there, which actually means to write. When we get our system interrupt, we're going to write out instead of exiting our program. But then we're going to move 1 into R0. In this context, when we're writing, it means to write to standard out, which is the screen, our monitor. So these registers all have special uses, right? R7 is what are we going to do? R0 is what's our return value, or in this case, where are we going to write? And then we'll do, we're going to move into R2 the value 25. This is the length of message to write. And then what are we going to write? We're going to load into register R1 the address of our message, which has been updated appropriately. So where to find the message. Okay, so this sequence of 4 commands says when we interrupt, we want to write to standard output a message with a length of 25. And so then we perform our system interrupt, SWI 0, which will actually write the message. And then to finish our program, we finish it just as we would before. We move a 1 into register 7, meaning exit the program on the next interrupt, and then we interrupt with a 0. So this is a nice long assembly program to perform Rot13 encoding and to print the decoded string to our screen. All right, so Control X or escape X. Let's save it with a yes. Save it to Rot13. Rot13.s exists. So what's a symbol? AS-O, Rot13.O, Rot13.s. Link, use our linker LD from an object file. rot13, rot13.o. And now we want to run it, and hopefully it works. So /rot13. Oh, there you go. The password is a secret. Well, sure looks like we decoded that. It's not gibberish anymore. What is one weird thing about this? And one thing we haven't really talked about is there's dashes in our output here. Why are we getting dashes? The original string didn't have dashes, right? Let's go look at it real quick. We're going to make one more edit here. Our original string here, no dashes. Why do we have dashes? Well, we didn't make an exception for spaces, so when we converted all this, look up the ASCII for space. It's decimal 32, right? 32 plus 13, what's that? 45. What's 45? It's a dash or a hyphen. So this is why we're getting dashes. Now, we didn't subtract 26 from this because 32 plus 13 is 45. 45 is less than or equal to 122, so we just left it alone. Realistically, though, we don't really want to convert spaces. So let's jump back in here and do one quick edit, and then we'll be done. What if we wanted to skip spaces? All right, well, let's think here. When do we actually add 13? When do we perform the conversion? It's this line. If it's a space, we don't want to perform that conversion. Right, we want to skip that. So let's check for spaces. Compare R3 to what? How do I check if it's a space? Compare it to decimal 32. Right? So compare R3 to 32. Is character a space? If it is, so branch equal, where should we branch to? Fortunately, we have a letter converted label down here. So this is basically saying if we have a space, then we want to do nothing to the letter. It's already converted. So let's branch down to our letter converted space where we just update the string. So if the character is a space, we skip converting it. Then we convert it. If it's less than or equal to 122, it's still in our good range, then we are finished converting it. Otherwise, we keep falling through and say, all right, well, we need to subtract 26 if we went past Z. So this should do it. Escape, or Control X. So we finished our program. Let's assemble it, load it. Again, up arrows allow you to go back to old commands, and then run it. And hey, it works. Right, spaces are no longer converted to dashes. So the password is a secret is done. So there's our encoded message. The password is a secret. We've decoded it. You can try this with as many different strings as you'd like. You can encode, decode. Your program will work. Just be sure you update the length of the string in your code. And hopefully it all makes sense. And I will see you all next time.